In this lesson, we will finish our discussion of descriptive statistics as it deals with bivariate data. We will learn about statistical correlation and its connection between two interval ratio variables. In the field of statistics, correlation refers to the measure of the relationship or association between two variables. When we talk about interval ratio variables, we are referring to variables that have a meaningful numerical scale and where the difference between values is consistent and interpretable. Basically, we are looking at the direction and magnitude of the relationship between two variables. This is often evaluated in a linear fashion in a graph called a scatterplot, where we plot one variable on the x-axis and the other on the y-axis. The graph is essentially a grid where each point on the plot represents the values of both variables for a specific observation. When examining a scatterplot, we look for the overall pattern of the points and their distribution across the plot. By observing the scatterplot, we can assess whether the variables have a linear relationship with each other. This graphical representation indicates the direction and the magnitude of the relationship. In a scatterplot, a linear relationship between variables is indicated when the points roughly follow a straight line pattern. That pattern indicates the direction of the relationship. If the line formed by the point slopes upward from left to right, as seen in this slide, it suggests a positive linear relationship. This means that as the values of one variable increase, the values of the other variable also tend to increase. Conversely, if the line formed by the point slopes downward from left to right, as we see in this slide, it suggests a negative linear relationship. In this case, as the values of one variable increase, the values of the other variable tend to decrease. Additionally, the spread or dispersion of the points around the line also provides information about the strength or magnitude of the linear relationship. If the points are closely clustered around the line, it indicates a strong linear relationship. Conversely, if the points are more spread out and do not adhere closely to the line, it suggests a weak or moderate linear relationship. There are other types of relationships that can occur between two variables. If the points on the scatterplot do not show any clear pattern or do not follow a straight line, it suggests the absence of a linear relationship. Instead, there may be a nonlinear relationship or no relationship at all between the variables. To determine the correlation between two interval ratio variables, several methods are commonly used, with the most widely known being Pearson's correlation coefficient. Pearson's correlation coefficient, denoted by the symbol R, measures the linear relationship between two variables. It assumes that the relationship between the variables follows a linear pattern. Pearson's correlation coefficient is calculated by dividing the covariance of the two variables by the product of their standard deviations. The resulting value ranges between -1 and +1, providing a quantifiable measure of the strength and direction of the relationship. Calculating the correlation coefficient is not easy, as you can see when you look at a sample calculation from this module's lecture notes. So, we will be using computer software to calculate the value of R in this class. When studying the correlation between two interval ratio variables, it is essential to distinguish between causation and correlation. Correlation does not imply causation, meaning that even if two variables are strongly correlated, it does not necessarily mean that changes in one variable cause changes in the other. Correlation only describes the statistical relationship between variables and does not provide information about the underlying causal mechanisms. We can take the correlation a step further regarding the value of R, with a mathematical concept called the proportion of variability. Explained by a correlation, it is referred to as the coefficient of determination and is often denoted as R squared. The square of the correlation coefficient, R, gives us the proportion of the variability in one variable that can be explained by the variability in the other variable. For example, if the correlation coefficient, R, is 0.60, the coefficient of determination, R squared, would be 0.36 or 0.6 squared. This means that 36% of the variability in one variable can be explained by the variability in the other variable. The coefficient of determination provides a measure of the strength of the relationship between the variables. However, it should not be interpreted as the proportion of causation or the proportion of the effect of one variable on the other. It simply quantifies the proportion of the variability in one variable that is associated with the variability in the other variable. The percent that is left is unaccounted for. There are other factors that could affect the outcome under study. Let's do an example of a correlation involving correlating sleep latency and asymmetric brain activity. Sleep latency is the amount of time it takes a person to fall asleep once they go to bed with the lights out. Asymmetric brain activity refers to differences in brain activity between the left and right hemispheres of the brain. Is there a correlation between the two? StatCrunch can graph and evaluate the correlation for us. Once we have the data entered into StatCrunch, one can start with graphing the data to see if there is a relationship. To create a scatter plot in StatCrunch, click on the Graph tab and select Scatter Plots. This will call up the dialog box where you can select your variables to correlate. In scatter plots, we typically put the dependent variable, the outcome, on the y-axis. Here our outcome, or our dependent variable, is the time it took our subjects to get to sleep, the latency. So we'll put sleep latency in the y variable and we'll put the brain activity, the asymmetry index, as the x variable. Just like our other plots, we can label our graph and edit the data display in the scatter plot dialog box if we choose. To make the fitted line on the plot, we click here on the polynomial order area of the dialog box, and we make it 1 for a first order line fit. That's a linear fit. Then click Compute, and the software will create the scatter plot for us that we can copy and paste into any report. So, here it looks like as the index increases, the subjects sleep much better, right? They fall asleep much faster, as denoted by a shorter sleep latency. We can have the software calculate the correlation, the R value, by clicking on our Stat tab, and then select Summary Stats. Then we can get the correlation value from Summary Stats menu. Here we see the R value calculated to be -0.90. That's a pretty strong negative correlation. According to this data, as asymmetric brain activity increases, sleep latency decreases. Let's do another correlation example. If we look at the discussion question again regarding birth weight, we can look at age and weight at the last menstrual period of the mothers. We can plot this data in StatCrunch once we load in that data set. So, if we plot age and weight at their last cycle here, again, we click on the Graph tab and select Scatter Plot. We get to the Graph dialog box. Our outcome here, the dependent variable, is going to be their weight at their last cycle. That's the LWT variable. So that would go on the y-axis. The age would go on the x-axis, so we place it as the x variable. After setting up the graph, we can even add a linear fit line. We click Compute and StatCrunch creates the graph. This plot shows that as the age increases, their weight at last period increases. This one doesn't look like it's tightly correlated, right? We can verify that by calculating the R value. We click on our Stat tab, and then select Summary Stats. Then we can get the correlation value from Summary Stats menu. Here we just select that age again and LWT for the weight. We see a positive correlation value that is weak at 0.18, right? There is a weak positive correlation between our subject's age and their weight at their last recorded period. The concept of correlation is crucial in understanding the extent to which changes in one variable are related to changes in another variable. It helps us to identify patterns, make predictions, and gain insights into the nature of the relationship between the variables under consideration. In the next module, we will extend our analysis to hypothesis testing and learn about how to make conclusions we see in our data.